Welcome back to statistics. In most real statistical problems, population parameters, like the population mean, mu, for instance, are unknown. And we need to estimate them based on the data that we do have. We've seen that confidence intervals provide a method of estimating a population mean based on sample data. We've seen how confidence intervals are computed in at least one case. And we've also had a little bit of a discussion about what confidence intervals mean and how they're to be interpreted. So now we'd like to deepen that discussion. And we're also going to consider a separate question, a related question. How do confidence intervals behave? That is, if you change certain things, for instance, the sample size or the confidence level, how do those changes affect the confidence interval itself? So let's get started. How confidence intervals behave. Let's begin with a quick summary of what we know about confidence intervals up to this point. To estimate an unknown mean mu from a population with standard deviation sigma, we take an SRS, a simple random sample of size n, and find the sample mean x bar. This sample mean is what we know as the point estimate for mu. But we're usually not satisfied with a point estimate because the point estimate is probably not exactly the value we're looking for. Rather, we'd like to have more information about how close we think the point estimate is to the population mean mu and how confident we are in that estimate. And that's precisely what a confidence interval gives us. Given a confidence level C, the confidence interval is an interval estimate of the form x bar plus or minus a margin of error, which I'm denoting here by m. So it's a range of values that extends from the sample mean minus the margin of error up to the sample mean plus the margin of error. The margin of error itself is computed based on the standard deviation of the sampling distribution of x bar. The z star that you see in the formula there is called a critical value for the confidence interval, and it simply specifies how many standard deviations of x bar are necessary in order to give us the confidence level that we desire. This technique can be used essentially whenever we can use the normal approximation for the sampling distribution of x bar. And we know that we can use that normal approximation in two cases. Either the population distribution itself is normal, in which case the sampling distribution will be normal for any sample size, or if the population distribution is not normal, we nevertheless know that the sampling distribution of x bar will be very close to normal as long as the sample size n is at least 30. So those are the conditions under which we can use this technique for computing confidence intervals. There's a further assumption here, which is that the population standard deviation sigma is known. We'll have to revisit this to deal with situations in which the population standard deviation is unknown. And the interpretation is that we have level C confidence in the interval estimate because the margin of error was chosen so that precisely C% of all x bar values have the property that the true mean mu is indeed within the confidence interval. So with that quick summary of what we know up to now, let's begin considering how confidence intervals behave. Maybe the first question that comes to mind is, does my confidence interval actually contain mu? Another question, what if a higher confidence level is required? How does that change the confidence interval? What if the sample size changes? How does that change the confidence interval? And what about the population standard deviation sigma? How does the confidence interval depend on that? We'll discuss all these questions in the upcoming few minutes. Does my confidence interval really contain the population mean mu? Let's begin by considering a little parable here of Jack and Jill. Let's say that Jack and Jill both take simple random samples of size 40 from the residential real estate listings in a large municipality. So they do this independently. They're going to get different random samples, but they're both of size 40. Let's say that Jack gets a sample average sale price of $133,000, while Jill, using a different random sample, gets a average sale price in her sample of $142,000. Assuming that sale prices vary with a standard deviation of $50,000, Jack and Jill can both compute a 95% confidence interval, right? That's because although we don't know that real estate pricings are normally distributed in this population, in fact, they're probably not. Real estate prices tend to be right skewed. Nevertheless, we have a sample size of 40, which is bigger than 30. So that means that we can use the techniques that we've discussed to compute confidence intervals. So Jack computes a 95% confidence interval, and it turns out to be his $133,000 mean sale price plus or minus a margin of error of $15,500. So Jack's 95% confidence interval goes from $117,500 up to $148,500. Jill, using her sample data, computes a confidence interval as well. It goes from her sample mean of $142,000 plus or minus, again, that same $15,500 margin of error. So Jill's confidence interval goes from $126,500 up to $157,500. Jack and Jill got different confidence intervals. And note, they both used exactly the same formula, which is the correct one, x bar plus or minus the critical value times the standard deviation of the sampling distribution, but they got different answers. So who's right? Well, actually, they're both right. They both applied the technique correctly. The only reason they got different answers was because they had different random samples, right? Different samples yield different sample means, and so the confidence intervals from different samples will be different. The margins of error will be the same as long as the sample sizes and confidence levels are the same. This is true, by the way, because we're assuming the population standard deviation sigma is known. And so how do we interpret this? Well, Jack and Jill both can be 95% confident that the mean is in their confidence intervals. The fact that they had different sample data just kind of comes with the territory. A confidence interval gives a range of plausible values for the population mean at a given confidence level based on the observed sample data. So if you have different sample data, naturally you're going to have a different range of plausible values. The margin of error for both Jack and Jill was chosen precisely so that 95% of all x bars lie within distance m, the margin of error, of the true mean. And therefore 95% of all 95% confidence intervals contain the true mean mu. That's why both Jack and Jill can be 95% confident that their intervals contain the true mean, even though their intervals are different. The same relationship holds for any confidence level. So for any confidence level C, the fraction of level C confidence intervals that contain mu is precisely C. I want to show you an app, actually screenshots from that app, that illustrate this process and this fact in a kind of a nice way. The app allows you to specify a confidence level, which I've done at 80% here, and also a sample size, and I've taken it as 20. The app assumes that the population distribution is normal, and you see that distribution in the left-hand panel there. It's the short, fat curve. The curve in black is the population distribution. The sampling distribution of X bar is shown in red, and it of course has a much smaller standard deviation because sample averages are less variable than individual measurements. What the app does is, at a press of a button, it'll take samples of the given size, so in this case 20, compute an X bar, and slap that margin of error around the X bar to form a confidence interval, just as we've done in our calculations. And you can tell whether the particular sample and the particular X bar that came from it result in a confidence interval that contained mu just by seeing whether that interval intersects the green vertical line there, which is the position of mu in the distributions. So let's take a sample of size 20, form the confidence interval, and see if it contains mu. Here we go. There you see it. The confidence interval is the sort of short, thick, horizontal black line you see there. The dot in the middle represents X bar from the sampling distribution. So in this case, you can see that the confidence interval does in fact contain mu because it intersects with that green line which marks mu's position. Those dark yellow dots you see under the confidence interval are just the 20 samples that were chosen for the SRS and that went into computing the X bar for this confidence interval. So you see those samples called out individually. They come from the population distribution, the thick, the sort of fat, short curve in black there. So those yellow dots are the individual 20 observations that went into this sample. So we've taken one sample, and that sample did result in a confidence interval that contains mu. I'm going to call that a hit. So out of one sample, so far we've got one hit, no misses. Let's take another SRS of size n equals 20 and compute the confidence interval and see what happens. So here we go. You can see this second confidence interval down below the first one. It's colored red now because it does not actually contain mu. Notice it has the same margin of error as the first confidence interval, but this time the X bar was just a little too far out in the tails for the confidence interval to actually contain mu at an 80% confidence level. So now we've got two confidence intervals in total, one hit, one miss, and our hit rate, the percentage of hits we've got, is 50%. If we continue this process, we'll see that hit rate start to settle down after many confidence intervals towards our confidence level, which is 80%. So let me just kind of click through a few of these. Here's our third interval. It wound up containing mu. So now we've got 2 out of 3 hits, or 67%. Fourth interval, again, failed to contain mu. So now it's 2 out of 4 for a 50% hit rate. 3 out of 5 after 5 confidence intervals. Now we got a 60% hit rate. 4 out of 6. 4 out of 7. We got another miss on trial number 7. 5 out of 8. And then 5 out of 9. We got another miss on trial 9. After 10 trials, we have 6 hits and 4 misses for a hit rate of 60%. And what the 80% confidence level means is that if I continue this process, looking at more and more confidence intervals, that hit rate will approach 80%. In fact, I'm going to run 10 now at a single click here. So now we have computed 20 confidence intervals in all, and 15 of them turned out to be containing the actual mean mu. So that's precisely a hit rate of 80%. And as we continue to take more, you'll occasionally get misses and occasionally get hits. The percentage will vary somewhat around 80%, but the variation will become less and less the more you take. So now I've taken a total of 100 different confidence intervals, and the hit rate is 78%, very close to our confidence level of 80%. After 200 confidence intervals, we've got a hit rate of 82%, again, very close. And it'll just get closer and closer the more confidence intervals we look at. After 400, we're right back at 80%. And again, this process would simply continue. So when we talk about the confidence level, that really is the fraction of x bars that will contain mu in their confidence intervals. And when you're talking about does my interval actually contain mu, the real answer is you don't know. But you're, in this case, 80% confident because you chose your margin of error so that 80% of all confidence intervals truly contain the mean. This is a nice little simulation to run through if you're just getting started with confidence intervals, and here's the web address. You can just click on that link and try it yourself. Okay, so that's a little bit about how confidence intervals change from sample to sample and the percentage of confidence intervals that actually contain the mean. Let's talk now about increasing the confidence level C. How does that change a confidence interval? Well, the first thing to realize is that increasing the confidence level C increases the critical value Z star. That's because Z star is chosen so that precisely your confidence level lies between negative Z star and Z star in the standard normal distribution. So here you see a confidence level of 90%, and that middle 90% corresponds to a Z star value of 1.6449. So my shaded area there would run from negative 1.6449 to 1.6449. And that's why 1.6449 is my critical value for 90% confidence. If I were going to increase that to 95% confidence, well, that region gets wider, and so my Z star has to get bigger. For 95% confidence, we find a Z star value of 1.9600. If I increase it further to say 99%, the Z star has to increase even further. For 99% confidence, your critical value, it turns out to be 2.5758. What would happen if you wanted 100% confidence? Well, as we know, the normal distribution never actually touches the x-axis. It's asymptotic to the x-axis, but it never gets there. So for 100% confidence, your Z star value would actually be infinity, and that's not realistic. So you really can't have 100% confidence in a confidence interval. But that Z star value does increase as the confidence level increases. And since Z star is the number of standard deviations of x bar needed for the margin of error, as you see in the formula there, increasing Z star increases the margin of error. So if you increase the confidence level, you ultimately increase the margin of error of the confidence interval. Now let's think a little bit about the sample size N. How does changing the sample size change the confidence interval? Well, we know that increasing the sample size decreases the standard deviation of x bar, right? Because the standard deviation of x bar is sigma divided by the square root of the sample size. So if you increase n, you increase that denominator, the amount you're dividing by, and therefore the result of the division gets smaller. This in turn decreases the margin of error because the margin of error is just a multiple of that standard deviation of x bar. So if sigma of x bar decreases, so does the margin of error. And therefore, increasing the sample size decreases the margin of error. In fact, the same relationship here holds as it did with standard deviation of the sampling distribution. You may recall that in order to have the standard deviation of a sampling distribution, you had to quadruple the sample size. Well, the exact same thing holds here, and for the exact same reason. If you wanted to increase the sample size so much that you have the margin of error, you'd actually have to quadruple the sample size. What about changing the standard deviation sigma? What does that do to the margin of error? Well, first of all, changing the standard deviation sigma isn't something normally we have control over. It just is what it is, as the saying goes. But you could rephrase the question, what if the standard deviation of sigma were different? How would that change the confidence interval? Well, increasing the standard deviation sigma increases the standard deviation of x bar, right? And it's from that same formula. If you increase sigma, then you're increasing the numerator of that fraction in the formula for the standard deviation of x bar. And so that would increase the result of the division. So that would in turn increase the margin of error for the same reason. The margin of error is a multiple of sigma of x bar. If sigma of x bar increases, so does the margin of error. So increasing the population standard deviation sigma also increases the margin of error. Let's summarize. A confidence interval gives a range of plausible values for the population mean at a given confidence level based on observed sample data. The fraction of level C confidence intervals that truly contain the population mean mu is precisely C. So 90% of all 90% confidence intervals do in fact contain mu, and that's why you have 90% confidence in the interval that you compute. Increasing the confidence level of an interval increases the margin of error for that confidence interval. But increasing the sample size that you use actually decreases the margin of error. And this is why statisticians like large sample sizes, because it gives you a smaller margin of error and therefore a more precise interval estimate. And finally, increasing the population standard deviation sigma also increases the margin of error m. So there we have it, a little bit more about confidence intervals and how they behave. There's a number of things still left to talk about. One of the most important is what we do when the population standard deviation sigma is unknown. How does that impact the computations and the interpretations that we have been discussing? We'll broach that subject very shortly. In the meantime, if you have questions, let me know. Stay safe, and I will see you again shortly.